Hi dear students, this is Bosef Solani, Assistant Professor, Department of Chemistry, Arts, Commerce and Science College, Jawahar District, Palghar. Dear friends, in the last part of the video, we discussed about the non-ideal solution or the real solution, which particularly shows deviation to some extent from the Raoults law. And it is observed that this non-ideal solution shows either positive deviation or the negative deviation from the Raoults law. And here we discussed about the two cases in the previous part of the video. Dear friends, in this part of the video, we are going to talk about the system which consist of the partially miscible liquids, means incompletely miscible liquid pairs in the system. And here in this case, we are going to talk about the pair of liquids which are miscible with each other only in a limited range of composition, and such type of liquid pairs which are miscible with each other in a limited range of composition, such liquid pairs are known as or are called as a partially miscible liquid pairs. And if we check these two partially miscible liquid pairs A and B, then some A dissolve in B and B dissolve in A, and at this stage we have two saturated solutions which form the two layers. One is the saturated solution of A in B and another is the saturated solution of B in A, and these two solutions are called as the conjugate solution, because we have the two components, two liquids A and B, and here in this case we are having the two saturated solutions. One is the saturated solution of A in B and another one is the saturated solution of B in A, and these two solutions are called as the conjugate solutions, and at a certain temperature these two layers can be completely miscible, and this temperature is known as consolidated temperature, or it is called as the critical solution temperature. So the solution at which these two partially miscible liquid pairs completely miscible, that temperature is called as the critical solution temperature. And depending upon the nature of liquids, the two liquid layers may become completely miscible by either increasing the temperature or by decreasing the temperatures here. And if these two immiscible liquid pairs becomes completely miscible by increasing the temperature, then such type of partially miscible liquid pairs are said to have upper critical solution temperature. And if these are completely miscible by decreasing the temperature, then these liquid pairs are called as or are said to have lower critical solution temperature. So this is very important, and there are some systems which found that this can in that case it is also found these systems have liquid pairs which are completely miscible either by decreasing or increasing the temperature, then the systems will have upper as well as lower critical solution. So in this way we are going to talk about the three types of the partially miscible liquid pair. One is the liquid pairs whose miscibility increases with the increase in temperature, and the systems having such systems are having upper critical solution temperature, and the liquid pairs whose miscibility increases with the decreasing temperature, and the systems are having the lower critical solution temperature. So phenol water system is the system having upper critical solution temperature, means the miscibility increases with the increasing temperature. Another one is the triethylamine water, and in this case this system is having a lower critical solution temperature. It means the solubility decreases with the increasing temperature, or the miscibility increases with the decreasing temperature. And there are some liquid pairs which has both upper as well as lower critical solution temperature, and the example is the nicotine water system. So dear friends, first of all we will talk about the first system which is having the upper critical solution temperature, means the miscibility increases with the increase in temperature. In this case, this phenol and water, these are partially miscible liquid pairs which exhibit the upper critical solution temperature, and it is observed that when the phenol is added to water, phenol goes into solution till its concentration reaches to 8%, and the addition of more phenol will give rise to two liquid pairs or the two liquid layers. Upper liquid layer consists of the saturated solution of phenol in water, and the lower layer consists of the saturated solution of water in phenol. So this is the important case. In this case, we are getting the two conjugate solution, and if this system or the conjugate solutions is again heated, then it is observed that the miscibility of phenol in water layer and the water in phenol increases with the increase in temperature, and finally at a certain temperature these two conjugate solutions are completely miscible with one another, and this in this case the heterogeneous solution becomes homogeneous solution, and this solution and this temperature is called as the critical solution temperature. Particularly it is called as the upper critical solution temperature, and this temperature is found, in this case it is 60 degrees Celsius for the phenol water system, so which is greater than the normal room temperature, and the percentage of phenol by weight is 36%. Here you can say this is the figure that indicates. So this is the graph of temperature versus mass percentage of phenol. So here this line indicates the saturated solution of phenol in water, and this is the saturated solution of water in phenol, and this point Q, at this point Q, the this system of two conjugate solutions are completely miscible with one another, and that's why the temperature corresponding to point Q is called as the critical solution temperature. It is the maximum of the curve, that's why it is called as the upper critical solution temperature. The portion above the line xy, it is completely homogeneous portion, and below the xy line it is heterogeneous, and this xy line is called as the lie line. So this point M indicates the solution of phenol in water, and this point y or N indicates the solution of water in phenol. So this is all about that I told you here. This here represents the composition of second layer, that is water in phenol, and here represents the composition of one layer, that is phenol in water. And this is the for temperature 45 degrees, which is below upper critical solution. Any liquid mixture outside the curve PQR, say at point Q or Y, corresponds to homogeneous, and below this it corresponds to heterogeneous. Already I told you. Another system which is having the lower critical solution temperature, and the example is triethylamine water system, and in this case the two liquid layers at room temperature, but their solubility or the miscibility increases with the decreasing the temperature. That's why these solutions or this system is having the lower critical solution temperature, and the example is triethylamine water system, which is having the lower critical solution temperature 18.5 degrees Celsius. So here below 18.5 degrees Celsius we are getting the two liquids which are completely miscible in all proportions, whereas above this temperature these two are separated from one another. Here this is the diagram that you can see. This line A B indicates the saturated solution of A in B, means the triethylamine in water, and B CB line indicates the solution of B in A. It means this is the solution of water in triethylamine, and there is solubility, mutual solubility goes on increasing with the decreasing the temperature, and at point B the two miscible or two partially miscible liquid pairs becomes completely miscible, and this is the lowest of the curve. That's why it is called as the lower critical solution temperature, which is equal to 18.5 degrees Celsius. So this is the important. So above this curve definitely two conjugate solution, and below this there is one solution. So below this line system is homogeneous, and above this point P system is heterogeneous. So this is same. Again, it is also observed that there are some systems which shows both upper as well as lower critical solution temperature, and the example is nicotine water system, and these liquid pairs are the combination of both upper critical and solution temperature and the lower critical solution temperature. And for such liquid pairs, the mutual solubility of the two liquids increases both by increasing the temperature as well as decreasing the temperature in a certain composition range. And the example is nicotine water system, which belongs to this category. Here you can see, here this system, so this is the point at which the two liquid pairs are completely miscible and the system will be homogeneous. So above this temperature, this is the maximum of the curve, that's why it is called the upper critical solution temperature. And this is also the point below which the system will be again homogeneous, but in between this part, definitely the two solutions will be separated from one another. Conjugate solutions or the layers will be separated from one another, and the system is heterogeneous. So here below this, at this point again, the system will have, or the two conjugate solutions will have the will be completely miscible with one another, and this is the minimum of the curve. That's why it's called the lowest critical solution temperature. So here system is homogeneous, and below this line also the system is homogeneous. That's why this system is said to have upper critical solution temperature and the lower critical solution temperature. In this case, so lower critical solution temperature is 60.8 degrees Celsius and the lower upper critical solution temperature is 208, and in between this temperature the system is heterogeneous, and below this temperature and above this temperature the system is homogeneous. So these are the three cases that we discussed in this part of the video to discuss the mutual miscibility of the two liquid pairs or the two conjugate solution in the systems which are having the lower critical solution temperature, upper critical solution temperature, and upper as well as lower critical solution temperature. So dear friends, in the next part of the video we will resume here. To discuss about some things regarding with the nurse distribution law and the distillation technique. So we will resume here to discuss about the nurse distribution law in the next part of the video. Thank you.